से बात करूं?
हाँ, अभी आप शुरू कर दीजिए इसका।
So this is a demonstration of शायद पीछे जाना पड़ेगा. Vertical. This is a demonstration of a level control process. The objective of this exercise is to maintain a level in tank B. And this is a tank with about 37 liters capacity. We have two tanks identical to each other. The water from this tank drains into this tank. So this is tank B, this is tank A. What we do here is we use a centrifugal pump and take suction from tank A and discharge this into tank B through the control valve. Now this tank B is a closed tank. It's not open to atmosphere. Hence, as you might have studied, for the sake of completeness, you must also realize that whenever we want to measure level in a closed tank, you have to use a differential pressure transmitter. So this is the differential pressure transmitter in question here. This DP cell is also fitted with the three-way manifold systems. Generally, whenever you see a differential pressure transmitter in use on board your ships, you will see this fitted with a three-way manifold system. And the way to use this is, it's got a high side and a low side. So you need to connect the high side to the higher water column and the low side to the lower water column. Now this is where your instructor comes into the picture, and he explains to you what is known as the two wet leg method of sensing water level. But anyway, for the scope of this discussion, we are going to take the output from this DP transmitter and give it to our instrumentation system that you are fairly familiar with by now. Okay, this too is a two-wire current telemetry system. So again, we are going to take the familiar jumper cables and connect them to power supply like we did before. That's the plus 24 volts. This goes to the plus indication of the transmitter. The minus output from the transmitter comes here, and we will check that against a meter. The minus of this returning back to power supply. And the moment we do that, you saw a slight displacement in the needle of the meter. Now I'm going to switch on a pump and wait for the water level in this to increase. Once it increases beyond 300 or thereabouts, we will see a change in the reading. Yeah, you can see the water level change. Now I'm going to switch off that pump, and we have some reading of water level which is now converted into an electronic form. So we're going to take these same two inputs, plus and minus, and give it back to our system. Yeah, if you remember, the engineering range of this unit was already set to 1000, and we have a set point of 300. In this particular case, however, we need to change the control action from reverse to direct. It is on direct, so we leave it as it is. Our set point is 300. We have the IP converter output, which has to be connected to the control valve. So our system is now complete, or our process control loop is now complete. And as you can see, since the water level is 624 and the set point is 300, the valve is already shut. So I'm going to change the set point to about 500, The valve is still closed, and then what we need to do is we need to run the pump, and then we need to drain the water in this. So I'm kind of loading the system, which will drop the water level. And as the water level is dropping, you should be able to see the output, which is presently at 100%, changing once the process value goes beyond or below 500. There the output is starting to respond, and you can see the control valve is modulating now. It has lifted to a slightly open position, and the water level has already reached 500. So this is a system under dynamic control, wherein the set point and the process variable are close to each other. As you can see, there is a continuous output, and the output of the controller is driving the valve to ensure that the water level stays close to the set point.
One more disturbance.
Okay.
One more disturbance will do.
Okay, I'm just going to increase the set point from 500 to 600 so you can appreciate the whole thing all over again. As you can see, the output that drives the control valve has gone down to 0. So the valve is completely open at 100% and the water level is rising. ये दिखाइए.
Yeah. And then the water level is.
Now as the valve starts coming, or as the process value starts coming close to 600, the output from this controller, right?
Correct. Oscillate हो रहा है, वही मैं देख रहा हूँ. Oscillation I am trying to capture in all three together. Again coming back.
तो अपन जैसा सेट करेंगे वैसे आ जाएगा.
Correct, correct, correct. Maybe stabilizing time, I think it will take. It will take some time for stabilization.
Take some time.
Yeah. So now I can talk about process dynamics, like it is taking time for. So we can speak about process dynamics.
Yeah, so the oscillation that you saw is a function of the process dynamics of the system. The process dynamics is the system's capability or the system's inherent time constant, so to speak. In other words, the system has got a certain inertia and it can absorb the energy at a particular rate. So different systems, smaller systems can absorb energy faster, larger systems will take some time to absorb that energy. It is this which is collectively known as process dynamics, and what happens as a result of process dynamics is the rate of these oscillations that you see will be different for different systems. It is for this reason that we need to configure the proportional integral and the derivative values for a particular application. As you can see, this system is more or less stable. And as you can see, the water level is far more steadier than it was before. Remember that this water level is steady in spite of the system being loaded or the system being on load.